2-mile-wide fragment of the comet traveling 40 miles a second.
Pieces of the comet that will hit Jupiter.
3 fragments are scheduled to hit the planet.
Will slam into the same area, the same spot on the planet Jupiter.
About 1993, we learned that there was a comet heading for Jupiter.
Comet Shoemaker-Levy 9 was a comet that was discovered by Eugene and Carolyn Shoemaker and David Levy. It was shown to be broken up into a bunch of pieces.
They traced back the orbit. This thing had gone by Jupiter and gotten disrupted.
And then they tracked the orbit forward and found out these are going to hit Jupiter.
And that got everyone excited.
It's really the first time that these impacts had been observed.
Impacts were very important in the formation of everything.
We could observe an impact on another planet.
Scientists still don't know what they're going to see tonight, but they do know that they've come to the best place in the world to see it.
The whole world community, scientific community, was preparing to observe these events.
Any telescopes that could observe the impacts did.
Many ground-based telescopes did.
The Hubble Space Telescope.
All of the images from Hubble that went on the Webb suddenly got everyone's attention.
Which was a real key to many of the scientific results.
Also Galileo,
which was on the way to Jupiter at the time.
The NASA Infrared Telescope Facility had a campaign dedicated to observing Shoemaker-Levy.
This observing run for the Shoemaker-Levy 9 impacts, that was my first observing run ever.
We're starting tonight with the near-infrared spectrometer.
God, that's gorgeous.
We were seeing something pop up on the screen. It was really shouting, literally dancing around. And we saw this bright thing just light up, and it was like, yes, we did it.
We were all like kids in a candy store, I guess.
A lot of the energy we saw wasn't just the impact itself, but it was the sort of splashback.
And when those pieces plowed into the atmosphere, they brought up big plumes of material that rained back down on the upper part of the atmosphere.
So we're able to measure changes in the upper atmosphere of Jupiter.
It taught us a great deal about how impacts take place.
Scientists say if a fragment the same size hit Earth, it would leave a crater the size of Rhode Island.
It was one of those wake-up calls that, not only are impacts something that happened in the past, but they're happening now in our solar system.
And here it is, this awakening.
It kind of precipitated this NASA Planetary Defense Coordination Office.
To make sure to find the asteroids that come close to Earth and the comets that come close to Earth, get them cataloged, figure out where they've been and where they're going to be in the future, just so we understand, are we at risk of being impacted on the Earth?
So that's a big component of what NASA does now, has planetary defense, to find potential impacts for the Earth and protecting it.
Let's go back to Senator Cruz's question. What would an asteroid that is a kilometer in diameter, what would it do if it hit the Earth?
That is likely to end human civilization.
The impacts of Comet Shoemaker-Levy 9 with Jupiter in 1994, that showed us that, impacts are still happening in the solar system today.
That really spurred some interest on the part of Congress.
NASA was tasked by Congress in 1998 to catalog 90% of all the large near-Earth objects, or those that are 1 kilometer or more in size.
Those objects are big enough to cause what we would call truly global devastation, meaning that they could cause global extinction events. The good news is that we found more than about 95% of them.
The catalog includes almost 900 asteroids, 1 kilometer or larger in size.
That said, none of these known large NEOs pose any threat of impact to the Earth within the next 100 years.
And then eventually in 2005, that direction from Congress to NASA was set to find the population of asteroids that are 140 meters and larger in size that could do regional damage should it impact Earth.
A city killer. Now the picture's not so rosy. We know of about 40% of those objects today.
Today, we do not have a complete inventory of all the possible impactors.
And that is something that NASA and the worldwide planetary defense community has been endeavoring to do.
Well, here at NASA, what I lead is the Planetary Defense Coordination Office. We are helping to coordinate efforts not only in the United States and across U.S. agencies, but also around the world.
Finding asteroids, tracking them, calculating their orbits, figuring out where they're going to be in the future, studying their physical properties, and then you get that information you might need in the event an impact threat is discovered.
We've discovered more than 30,000 near-Earth objects so far, and we're discovering hundreds, every year.
But we haven't found them all, so that's really the big question. There's almost certainly a decent-sized asteroid out there that is going to pose an impact threat to the planet. We're just trying to find it right now. So the way we approach finding near-Earth objects is basically just to make a short movie of the night sky that consists of 4 frames. And then our software will pick out objects that are moving inside of the 4 frames, and we have to identify if they are real or if they are false detections. I first started hunting asteroids in my backyard, and I just had the hope of maybe discovering one. And when that happened, it was a very special moment in my life. My interest in astronomy started at a fairly young age. I remember as a kid seeing comet Hale-Bopp in the sky from southern Utah. It was really a spectacular sight as a child, and just trying to wrap my mind around what I was looking at was difficult. This is one area of science where discoveries are still happening on a nightly basis, and it's really a neat feeling to step into that, where you can be sitting at a telescope at night and discover a new minor planet that's in orbit around the sun that nobody has ever seen before. It's a special thing, and I think that's what draws a lot of people into this business.
The first order of planetary defense is finding the asteroids. And so one aspect of the program is funding institutions with telescopes that can image wide swaths of the sky to be able to look at the starry background and look for objects moving with respect to the stars to see is there something there that we haven't seen before.
This is the whole sky. That's an all-sky camera. So you can see this is a live video feed from the end of the telescope, and you can make out the Milky Way right here. And this is the size of the images we're taking right now. And then we subtract the known objects and the stars from those images, and then we look for moving targets.
The object is moving because it's closer to the Earth than the background star.
I can tell this first one is a star. You can see that that object stays there. So if I load up a catalog image, which is a very old image, you can see that first hit is actually a star. That one's actually a star. Those moving targets are going to be asteroids that are in orbit around the sun. So that's a known asteroid. It comes up green, and it has the designation above it. And oftentimes they're new. We've never seen them before. So what we have here is a near-Earth asteroid that is likely brand new. And I can already tell that it's not coming up in any of the known databases.
And then what you have to do is go and identify whether it's a known asteroid or a new asteroid. So that's the next step.
When the asteroid is first discovered, we submit the information almost immediately to the Minor Planet Center at Harvard. And we are going to send this data off in real time here. The temporary designation we're going to assign to it, the date and the time, and the location on the sky that it was located, and then its approximate visual magnitude. I'm going to report it as a brand new near-Earth object candidate.
It's important to turn that information around quickly. The different survey telescopes quickly feed those position measurements to the Minor Planet Center, which is the internationally recognized repository for position measurements of small bodies throughout the solar system.
Minor Planet Center I like to think as the link between the astronomy community and everything that comes after that in planetary defense. My name is Federica Spoto, and I'm the project scientist of the Minor Planet Center. So part of the role of the Minor Planet Center is to actually distinguish what is known and what is not known. We keep all the observations and all the orbits of the objects. So we don't see the image, we just see these points, and those represent the different position of the object moving. And so it tells you very accurately the time of the epoch of the observations, and then the position. So once we have the position and the time, we can get the orbit.
So all the data comes in from everyone, gets consolidated there. So we have a common catalog that we are working from.
An archive of everything that is known and everything that is not known. The cool thing about the Minor Planet Center is that everything we do is public. So as soon as we receive the observations goes out.
That information can all be rolled up there and available for other observatories to see them and then go get additional observations so that there is enough information to get an orbit.
And anyone can then access that data to track these objects down and help us determine if they are going to be an impact risk in the future.
Once we find an asteroid and we've got an orbit for it, the next logical question is it going to hit the Earth?